Okay, let's have problem number 3 for the normal stress. So the problem states that a rod is composed of an aluminum section rigidly attached between steel and bronze section as shown in our figure. Action loads are applied at the positions indicated. So if P is 3,000 pounds and the cross-sectional area of the rod is 0.5 inches squared, determine the stress in each section. Okay, for this problem, you are given with a section of a rod. You have the aluminum section which is connected to the steel section and the bronze section. You have the applied force on the steel section and of course on the aluminum section. So for this one, you have your 40 indicated as 40 and you have your P on at the end of the aluminum section. So if P is equal to 3,000, so therefore this can be equivalent to 12,000. And of course, this one is equal to 3,000. So if we're going to draw our FBD or the free body diagram for this one, so we can identify the internal forces on our rod section. So for this one, so since we have on the steel section, you have the steel, this is our aluminum, and this is our bronze. So from the steel section, of course, you have the applied load, which is 40, and that is equivalent to 12,000. Or this can be equal to 12 kips, and this is equivalent to 3 kips. So if we're going to draw our FBD, so we have now our internal forces. So start with, on the steel section, of course, this is our 12K towards our aluminum section. And of course, in the bronze section, you have 3,000 pounds or 3 kips. So that's one, we go down by 3. So you have now your FBD for our rod section. So this one is 12 kips, and of course this is equivalent to 9 kips. So that's one is 9 kips. So using this internal forces, we could identify now the stress on the steel, aluminum, and on the bronze. So let's start with the steel. So of course the formula is stress is equal to P all over A. Of course, from the formula, stress is equal to force all over A, or P all over A. So substituting the equation, the given value for each, for P and A. So our P here is equal to 12. And of course, our area is given, the area of the rod is 0.5. So we have the 0.5. So if we try to get now the stress on the steel, we have here 24 KSI. And if we're going to have for the aluminum, of course, stress on the aluminum is equal to P all over A. So therefore, you can have here, steel, this is 12, all over 0.5, and simply we have the value which is 24 KSI. And lastly, for the bronze, if we're going to have the bronze, we can have stress for the bronze equal to P all over A. So therefore, you will have here equivalent value, which is, this one is 9 all over 0.5. So therefore, our stress on the bronze is equal to 18 KSI. So we have now the value for our stresses for the steel and for the aluminum, which is 24 KSI, and for the bronze 18 KSI. Okay, we have here problem number 4. A 12 inches square steel bearing plate lies between an 8 inches diameter wooden post and the concrete footing as shown in the figure. Determine the maximum value of the load P if the stress in the wood is limited to 1,800 psi and that in concrete to 650 psi. So we are given here with our figure. So you have a wood, you have a concrete. On top we have a wood which has a diameter of 8 inches, and we have a concrete which has a dimension of 12 inches. So we have an applied force P. So what will be the value? What would be the maximum value of the P if our stress in the wood is limited to 1,800 psi and that of the concrete is 650 psi? So from here we have to investigate what would be the value for our maximum load. That will be the safe maximum load that will be applied. So therefore, if we're going to have the free body diagram for our wood, so if this is our wood, so you have here our P, applied force, and of course you have the force exerted by the wood. In this one, the force exerted by the wood, of course, is equal to stress multiplied to the area. And of course, in our given problem, our limiting stress for the wood is 1,800 psi and multiplied to our area, which is pi d squared all over 4, and this is 1 all over 4 times the diameter is 8 inches. So therefore, if we try to simplify this one, this is equivalent to 90,477.9 pounds. From our FBD, from this FBD, from our equilibrium equations, so we can have summation of forces vertical equal to 0. So we need to say P is equal to piece of W. So therefore, our P, the applied load, is equal to 90,477.9 pounds. Now let's have the free body diagram for the concrete. This is of course for the wood, and for the concrete, so we'll have here our wood on top where the applied force is acting, and of course on the second layer we have our concrete, and of course you have the force exerted by the concrete denoted by P sub C. So for the concrete, if we're going to have the force exerted by the concrete, of course stress times area. And this is equal to, the stress is, the limiting stress of the concrete is 650 psi multiplied to the area. The dimension is 12 inches by 12 inches. So therefore you will have 12 raised to the second. And this is equivalent to 93,600 pounds. So therefore, from the FBD or from the free body diagram, we can have our summation of vertical forces equal to 0. So our P is equal to P sub C, and this is actually equivalent to 93,600 pounds. So therefore, we have now two values for P. We're going to select which one is the maximum value of the load P. We're going to choose, our selected value for P is our safe load. So therefore, if we're going to choose from these two values of P, our safe load, since we're talking about safe load, so the smaller value, which is equal to 90,477.9 pounds, or simply that will be 90,478 pounds. Okay, let's have problem number 5. For the task shown in the figure, calculate the stresses in members D8 and DF. The cross-sectional area of each member is 1.8 inches squared. You have to indicate tension or contraction. Okay, we're required to compute for the stress at DE and DF. So to start with, we are going to get the value for our reaction force at joint F. So what will be the reaction force? So summation of moment at point A equal to 0. So what will be R sub F negative, since this is in a counterclockwise direction, multiplied to the moment arm distance, 24. Then plus, you have here 30 kips, so 30 times the moment arm distance, which is 16. Moment arm distance, this is 16, equal to 0. So simply, you can have here R sub F is equal to 30 times 16, and this is over 24, and it gives us the value of 20 kips. So we have now the value for our reaction force at point R. So what will be the force at DF? So let's have joint F. So if we're going to have joint F, we have the free body diagram. Of course, you have the forces acting, R sub F, and let us have assumed compression for DF. And of course, the slope is 3, this is 4 and 5, this is 6 and 8. So simply, it can be simplified as 3 and 4. So therefore, if you then have the summation force vertical equal to 0, so you have R sub F, then minus above, downward dF is the vertical component, dF multiplied to a slope which is 3 all over 5 equal to 0. So therefore, dF is equal to, substitute the value of Rf, which is 20, so times 5 all over 3. So this gives us now the value of dF, which is 33.33 kips. And now for our dE, so what will be the value for our dE? So therefore, if you're going to have here the value for dE, this is at joint E. So at joint B, so let's have joint B rather. At joint B, so we can have here our forces. You have our force DD, you have our force DF, and of course the slope, this is 3, this is 4, 5, this is 4, 3, and 5. Of course, you have your downward, let us have assumption downward DE. So therefore, summation of forces vertical equal to 0. So we can have here upward dF, so dF times 3 over 5, then plus dD, which is 3 over 5. So then we have minus dE, so equal to 0. So we can have here dF equal to dD, so therefore we can have 33.33, 3 all over 5 times 2, then minus dE equal to 0. So therefore, our dE is equal to, the value here is 39.99, or this is simply 40 kips. Since you have now the forces of dE and dF, we can complete now for the stress. So what will be the stress at dE? So therefore, simply have P all over A. So we have here 40 all over 1.8, and it gives us the value of 22.2 kips. And of course, this is in tension. This is in tension because we assume here we have a tension force, and the result is positive, so we have the correct assumption. So therefore, this is in tension. So what will be the stress at dF? Of course, you simply have force all over area. You have 33.33 all over 1.8. So the stress at dF is equivalent to 18.52 kips, and of course this is in compression. So we have now the value for our stress at dE and